Good evening, everyone, and welcome to Zoom into Physics number 14. And this time we're talking about how light travels through Christmas lights. And so we'll be focusing on that this night. We have a wonderful panel of 4 people. Before that, I will acknowledge the traditional custodians of the lands on which we're all meeting. And some are overseas, so I wonder how that works. And pay our respects to the elders, past, present, and emerging. So, without further ado, let's launch into introducing the panelists tonight. So let me head off with Tibor. Oh, there is a question. Sorry. Each time the panelist introduces themselves, they have to answer the introductory question. And the introductory question this evening is: what optical phenomenon most intrigues you, and why?
Okay. Well, thanks everyone. I'm Keke Molnar. I'm an associate in the Department of Philosophy at Sydney University. I pretend to be a philosopher of science, and I ask all the funny questions. My job on the panel is to annoy everybody. My favorite phenomenon, optical phenomenon, is birefringence. You may or may not have heard of it. I can't even pronounce it. But it's a really interesting property of crystals. In particular, I have a piece of calcite crystal here at home, and you shine ordinary light into it, and 2 beams of light come out, one polarized one way, another one polarized the other way. And I think it really reveals lots of interesting things about what light is or isn't, and how it works, and how crystals work. I think it really is a profound phenomenon. So I find it more interesting than rainbows.
Thanks, Tibor. Geraint, let's move on to you next.
Hi there. Yeah, so I'm Garrett Lewis. I'm a professor of astrophysics at the University of Sydney, and I study both theoretical and observational astrophysics, cosmology, try to understand the universe. And I think my favorite phenomena attached to light is this notion of gravitational lensing. This thing that came from Einstein's general theory of relativity, that light rays, when they travel to the universe, don't travel in straight lines anymore, but gravity can distort their paths. And so a massive object can behave like a glass lens, and so gives us an opportunity to magnify the very distant universe. And anybody who's seen any of the recent images from the James Webb Space Telescope, the JWST, would have seen this in action, where we are getting these highly distorted views of the distant universe, but things are so magnified, we are seeing things that we would not be able to without this natural telescope.
Thank you. And one of our guests is running a little bit late this evening. So Kirrily, I wonder if you could introduce both of you.
Oh. Yeah, sure. Okay, so I'm Kerry Rule. One of the reasons why Scott wants me to introduce both of us is that both Kerry Brenner and myself work for ANSTO. I'm located in the Neutron Scattering Division, whereas Kerry is in charge of the Center for Accelerator Science, so looking at ion implantation and that sort of thing. My work with neutron scattering is focused primarily on investigating dynamics in materials, how atoms might move, or how particularly magnetic materials, how we can manipulate magnetic spin directions for possible future technologies in spintronics and low energy electronics. So to answer the question, I've actually got 2 answers, so that's good. I'll answer for Kerry as well. I think one optical phenomenon that I've always just clicked with is Young's double slit experiment. So if you all remember that, this was an experiment performed in the 1800s, like 1801, I believe. And Thomas Young essentially sent light through a double slit. And the question was, is light performing as a particle or as a packet, or is light behaving like a wave? And as an extension to this, about 100 years later, de Broglie did the same thing with electrons and showed that electrons, which we normally think of as a particle also showed these wave-like behaviors. And this really opened up the realm of wave-particle duality and quantum mechanics in terms of trying to understand propagation of energy. I would call these all energy. So that was my first one that I've always loved. And I love the simplicity of the experiment, that you can do it at home if you have the right setup. And the other thing I'll throw back to Tibor, I really love rainbows. And particularly the fact that rainbows are not just arches, but they're actually circles. So when you this is something that perhaps I learned quite late in life, I think. Certainly I never knew this as a kid. It's only more recently that I learned that if you go up high enough, you don't just see the arched rainbow, but you see it as a full circle. And that's brilliant. And you've got to have the right conditions. You usually see it in the afternoon because the sun's got to be low in the sky. You've got to get the right angle of reflection. But yeah, I think rainbows are fascinating, Tibor. Sorry.
No, that's fine. As I think it was Richard Feynman who said that if you can explain the double slit experiment, you can explain absolutely everything about quantum mechanics. All the secrets of quantum mechanics are in that one experiment, and nobody understands it. It's a fascinating show. I agree.
Can I just jump in very slightly at this point? We're just talking about the double slit and light behaving as particles and waves. And I think it's important to mention the Braggs, who were a father and son combination who both won the Nobel Prize. The father, if I get this right around, the father for showing that photons were particles, and the son for showing that photons were waves. And they did that work, I think, when they were in Adelaide, when they lived in Australia, if I got my history correct.
William Lawrence and William Henry Bragg.
Correct. Yeah, that's it. So, there's a bit of Australian history there as well.
100%. And, I do Bragg scattering every day as part of my job. So that's one other reason why I think I resonate with the Young's double slit, the first sort of experiment to show that sort of thing. More than 100 years before the Braggs did. So, yeah.
And on that note, congratulations, Kirrily, on your recent Neutron Scatterer of the Year award. And person who has scattered the most neutrons in one calendar year, or something like that.
Something like that, I'm sure.
Congratulations. Let's launch straight into the topic. We've already started, and so what is the nature of physics that allows light to travel through a solid? What is transparency, and what are the basics of it for those people who are new to physics? Does anyone want to try to describe it in a nutshell?
Well, I guess I can narrow the question or broaden the question, depending on how you want to look at it, by observing that lots of materials are transparent, even the ones you can't see through. And the point is that materials they transmit or allow the transmission or propagation of light of some wavelengths or some frequencies, but not of others. So just because we think something is opaque, it doesn't mean nothing goes through. Other kinds of light waves, be they radio waves or X-rays or something else, they can go through those materials. It just so happens that visible light can't go through. Visible light is a very, very small part. On a geometric scale, it's only about 2% of the width of all the different wavelengths and frequencies of light that we have. Radio waves, X-rays, these are all light. They're all exactly the same kind of wave, the same kind of, I won't say material, substance or anything, I don't know what they are, but they're all the same kind of thing. The only difference between a radio wave and an X-ray and a red light and a green light is that they have different wavelengths. And we have eyes which are sensitive to a very, very narrow band of light in a particular wavelength, which just happens to be the wavelength that the sun gives out most of its light. That's probably not a coincidence.
I'd read that the reason we see in the wavelength that we do is because it travels through water, and the first eyes were when we were still in the sea. And so it's where our eyes evolved to be the color sensitive to the colors that go through water, which makes sense.
Yeah, it also makes sense that it happens to be the light at which the sun emits most of, because after all, they light up the Earth.
No, go on, Geraint. Get in there, mate. Get in there, mate.
Well, I think it's a false analogy to say that there's a link between the evolution of what we can see and the output of the sun, because firstly, the output of the sun is a complicated thing. It is not the simple curve that people imagine it to be. So when people say it peaks in a particular wavelength, that's not strictly true. As you mentioned, Scott, it's more to do with the materials and the molecules available than the spectrum of light that was arriving on Earth. They do have to be intertwined, but I think it's more of a lucky coincidence than our evolution was driven by precisely where the sun peaks in a particular curve with a particular representation of the output of the sun.
So when a material is transparent, does that mean that the light just goes through without touching the sides, as it were? Is there no interaction going on, or is it a sort of a photonic pass the parcel?
So I'm happy to jump in with some physics. I think the important thing to start with is light traveling through a vacuum, right? So we talk about how light goes from one place to another, and James Clerk Maxwell told us that we should think about light as an electromagnetic wave that travels from one place to another, and in a vacuum it sort of self-propagates itself along. And then the question is, then what happens when that electromagnetic wave hits a material? And of course, an electromagnetic wave interacts electromagnetically, which means that it has something to do with charges. So whatever's going on has to do with what happens to the charges in the material. Either the material can absorb some of that wave and re-emit it, or it can't absorb some of that wave because the charges can't respond. And so it all comes down to what happens to the electronic charges inside the material. How can they respond when the electromagnetic wave tries to propagate through it?
So would you then say in a vacuum, if there are no electrons for it to interact with, that light will just continue straight, will just continue traveling the packet?
Absolutely. And of course, some of my work involves the cosmic microwave background, and that includes light rays that have been traveling for basically 13.4 billion years. And those light rays have traveled across the universe, and there hasn't been enough charges in the way for there to be any interference with its propagation.
So is the concept of like a billiard ball type photon just completely unuseful, and we should just focus on the waves?
What do you want to do with it? I mean, I'm going to be treading on the philosopher's toes any second now, I'm sure. But when you want to think about the picture of what light is, what is it that you want that picture to convey? So when light travels, it travels as a wave. So when Kirrily was talking about the double slit experiment, light always travels through that apparatus as if it's a wave. But when light interacts with something, such as like one of the Bragg experiments where something gets all the energy of the wave in one particular place, it looks like a particle. So when you say, which way do you want to look at it, it depends what it is that light is doing at the particular time. Is it traveling or is it interacting?
Yeah, when it interacts with some matter, what happens is the energy of the wave, the energy of the light, is transferred to that matter, and the wave of light, if you like, the particle of light, delivers a quantum of momentum to the thing that it interacts with. Now, it's perhaps useful to think of it as a particle because typically we think of particles that carry momentum. But I think that's about the only reason for thinking it. It certainly isn't a little ball bearing. It's not a little ball, just the same way as electrons are not little balls. In fact, there are no little balls anywhere in physics. I think the whole story of physics is completely wrong if you think of it the way you were taught in high school, where everything was made of little balls going around in circles. Sorry?
It's simplified. It's an
Of course it
approximation.
is, yeah.
Everything is
Of course,
approximation.
but now we know that it really isn't that. That's a rather weak approximation. We can have slightly more nuanced approximations now. So no, I don't think light is a particle. Light is some sort of energy, and it propagates through a vacuum. I don't know quite how it does that. We can argue about whether a vacuum is empty or not. I don't think vacuum is empty. In fact, what I think, and now I'm going to step on Geraint's toes, what I think is that the ether theory is slowly coming back. It's sneaking back in through the back door, because now we've got a Higgs field and a gravitational field. We have so many fields. All those fields added together pretty much add up like an ether. There's some sort of thing out there which is all these fields, and everything plays out in these fields, much the same way as we used to think of there being an ether through which light propagates and everything else propagates. Now we just have a sea of fields. It's not the same sort of ether as Michelson and Morley couldn't find. I understand that, but it's I don't know. I don't think the ether theory has completely gone away in one way or another. What do you think, Geraint?
Okay, so I'm going to quote another physicist here. So I'm going to quote Einstein. So Einstein was asked to describe the wireless telegraph, and he said that, you know, a telegraph is like imagining a cat across the country, and you pull its tail and its mouth goes meow, and the wireless telegraph is exactly the same but without the cat, right? So the problem with the ether was this notion that light needed a thing to propagate in, is that we thought that these waves had to be physical waves in the same ways that water waves are physical waves, that there was a displacement and a restoring force, etc., right? If you do away with that picture, i.e. you now say that they're quantum waves, which are oscillated in quantum fields, which only exist in quantum land, they are not bound by the same kind of physics of materials, then you no longer have to worry about that. So that's the get out of jail free card that physicists use, not to worry about the fact that quantum waves don't require an ether, because quantum waves don't require an ether, right? It's a circular argument.
Anyway, it's an interesting question as to what light is.
Yeah.
It's unlikely to be a little ball bearing. It's not a wave the way that waves in water are waves. I think Geraint's quite right about that. But I'm not sure that
my description, Tibor, whenever I talk to students about this, I say light or a photon is a packet of energy, and it's quantized, so it's got a discrete energy. So you know, the packet is full. And then the way it moves and the way it interacts, well, again, that depends on what you're measuring and how you're measuring it. But I don't think it's constrained, like Geraint was saying, to any medium. You know, it's not like water waves are constrained to the planar water that they're sitting on, but light is not constrained. And so the idea of, does light travel in a straight line? How does it go through a apparently transparent material is an excellent question. You know, how does it behave as it's interacting? Remember, it's a packet of energy. It's not a ball, it's not a wave, it's just a packet of energy. We're physicists, everything is energy.
Well, and I'm a non-physicist, and I have no idea what energy is, even though I read Richard Feynman's simple explanation of it in his Feynman lectures 3 or 4 times. I got no idea what energy is. I'm giving up on that one. My imagination is limited. So then to describe, well, you might as well be talking about potentials. No, there are such things as potentials. What the hell are they? Okay, to me, it's just physicists talk or mathematicians talk to do the calculations and stay obscure and occult from the rest of the world, because we lay people we can't grasp what we can't grasp. Some of us really want to, and it's a bit unfair that some people only go so far in helping us to understand. Go ahead.
So may I jump in? So are you worried that that like myself and Kirrily and Scott are in some sort of cabal and we?
No, I'm just trying to be funny. I'm sorry. I'm just trying to be humorous.
Okay.
I'm just using this language for the sake of drama. I don't know. No. I'm just saying that I'm trying to make light of my ignorance, I guess.
I think what you're hitting on, Mark, is language is so important. Using the right language so that it doesn't confuse people. And I think, going back to what Scott was saying originally about having the billiard balls, can we describe things by billiard balls bouncing off each other? Well, that's one way to describe them, but is it really what's happening? And I think if you delve deeper or you deep dive.
Oh, you've lost your microphone.
Oh, sorry. I should hold this back up. If you deep dive down, no one really knows exactly what's happening, but we're just describing it using different language. So it's language that's key to trying to understand.
Yeah, and I love that by digging, scientists dig down deep, and they are as much waist deep in mystery as anyone else, which is wonderful. I came here thinking, well, perhaps all these people have done the research for this meeting. They know they're not going to call on anything, so they know what light is and how light works. So I don't have to worry about asking any embarrassing questions that people won't know. No, apparently it is as mysterious, still continues to be sufficiently mysterious as to be worthy of a topic of discussion tonight. So that's great.
But that's why we're all here.
I've noticed that Kerry has just joined us. Welcome, Kerry, and we have said that you would be joining us. And maybe would you like to introduce yourself and answer today's panel question, which is which optical phenomenon most intrigues you and why?
Evening all. Yes, what a wonderful part of the conversations to jump into, because I think we've already got into the thick of it already, so that's great. I love it. Hi everyone, I'm Kerry Brenner. I'm a physicist at ANSTO Centre for Accelerator Science. I'm a laser plasma physicist by trade and accelerator scientist in day job at the moment. And yes, light, well, I ended up spending a lot of time thinking about light, extreme light, and what it does to things and its interaction with matter. That was the basis of high-powered laser plasma science. But really, actually, I'm glad, Kirrily, your background, because I guess my link into asking about the world and how it really works, and then continuing to ask more and more questions right through to where I am now, is all kicked off by rainbows and refraction. It's plain and simple. So there's no stronger way to convince people that light does interesting things and energy in this form does things that seeing is believing with that. I think that's why it was my entry point into asking what's going on. How does that work? And the basic, when people, because rainbows are taught right at school, right, as well. You talk about prisms and things, all very hands-on, and that's what the kids learn. They look, white light is a rainbow and what that means. But and it seems quite a simpler thing when you look at it at school, but actually the principle of refraction, I think that's what we were getting to. Is this the part of the conversation that I was in now? That what's really going on? It's not a line of little mini light particles going through and suddenly changing direction. There's something a bit deeper going in there, and that's why it carries, I think, a lot of principles of electromagnetic interaction, and you can talk about it in photons, you can talk about it in waves, so for me, I think it is quite symbolic of a lot of the depth and complexities, but at the same time, there's also, we were just talking about language, weren't we? About there is a way, a version of explaining what's going on, which can be understood by everyone. You don't need to have a PhD to be able to understand what's going on. Yeah, and I think at the extreme end of laser plasma physics, there's some weird and wonderful things around refraction that go on when you're playing with lasers with a very narrow bandwidth, but there's still some really funky things when you start shooting them into high density plasmas. Yeah, it's still a very interesting phenomenon, really, at the extreme end, as well as the simple end of light going through a prism or a raindrop. That's the more poetic one about rainbows, isn't it? And I'm glad, I was just reading on the chat as well, we're talking about someone who'd seen a true rainbow, a circular rainbow. Yeah, that's fantastic. I've been on many flights and never been lucky enough to be at the right time or at a window seat at the right time.
Or have I? I'm hanging out for it, but Mary was lucky enough.
One of the most interesting phenomena that I've read about, I haven't seen it, reminds me of what you were talking about, Kerry, about shining very intense lasers of energies of 250 GeV and that sort of thing. And apparently, if you shine a couple of these onto each other, you can actually get electrons and positrons to pop out of the mix. So you can, in fact, create matter. You can create particles that we recognize as electrons, which we think are matter particles. We can create these out of nothing but pure light. You just get two laser beams, shine them at each other, and bingo, you get you get electrons and positrons popping out of it. And I think that also says something very interesting about what matter is, about what we think electrons and other particles are, because they're somehow more closely connected. It's not like we've got energy and we have matter. We don't have that dichotomy in the real world. Somehow that model just doesn't work anymore, and we have to think again. We have to dig a little deeper to find out what's going on.
Yep, so that's a series of experiments called breaking the vacuum. And that's actually something that is proposed with petawatt and several petawatt class lasers. And there are a couple of experiments in the previous place where I used to work in the UK, the Central Laser Facility. There were a couple of people who did those experiments. And unfortunately, the power and intensity of the light is just below the threshold where you really would be able to see this experimentally. But with several petawatt, say, I think it's 4 or 5, but certainly 10 petawatt lasers, which there is one coming online in Romania at the moment. You focus that down and you'll get to the peak laser intensities you'll get if you can then interact them, overlap them perfectly.
But it hasn't been
Femtosecond, temporal and submicron spatial overlap, which is not easy with these laser systems. If you can achieve that, then you can. My understanding of what was going on there is really that while the vacuum, we in normal talk about vacuum being empty, in the fabric of space-time, it's actually a combination of lots of particles and antiparticles continuously annihilating, and what the intense photon interaction, you're generating extreme density or concentration of photon and laser intensity that actually then directly accelerates those particles, and they're accelerated away from each other in a time that's quick enough before they annihilate. So you're popping out particles from the vacuum. I don't know why I'm doing this. The fabric of space-time, you're using the laser as a particle accelerator, and you're able to accelerate those particles or those electron-positron pairs away from each other before they've got time to annihilate. So that's why the extremity in terms of time, you need femtosecond duration and an extreme laser intensities to actually transfer enough energy to the particles that they get away from each other.
But you're not generating particles out of photons alone.
Well,
There is a transfer of energy between the photon cloud to the particles, but the idea is that the particles are there all the time. It's just that they're constantly annihilating and turning into energy of the.
Yeah, because I when Tibor was saying what he was saying, I was incredulous. I mean, I don't know, and I haven't read. I mean, I don't know, but it didn't sound like it. It just sounds counterintuitive that light, just light, at any intensity can produce matter at all. Now, I was starting to wrap my mind around it and starting to believe you, Tibor, but then, you know, thank goodness, I think Kerry has saved me from that twisted brain. And I think that possibly what you're saying is that we're not creating, the theory is not that you can create actual matter out of actual photons alone, but that matter comes out of, I don't know, the ether or the.
Well, but then, Mark, we have to explain the opposite as well, because we know that if we get a positron and an electron and we bump them into each other, they annihilate, they go to nothing, or they go back into the vacuum and they become part of the background. I don't know which of those happens, but one of those two things happens. And you get in return 2 photons of light, the energy of which happens to be the energy which matches the energy of the positron and the electron that you started with. So in a way, perhaps I'm speaking loosely, I don't know. I don't know. I haven't read anything about what goes on exactly at the point of annihilation, but it does read like we are converting matter or particles, electrons and positrons, into photons.
Yes, but
Well, they're conserved though. They're conserved. It's just that they sum to zero.
Sorry?
I think so if you start off with the electron and the positron, then if you sum the two masses, it's zero, right? So you've just got zero mass to begin with and zero mass to end with. And the same true with what Kerry was saying. You just come in firstly with a crap load of energy, and you can turn that into positive mass and negative mass. And as long as they're equal and opposite, then you don't violate any conservation laws. Is that? It's
got the 2 photons that you get are each 511 keV. It's not that one is minus 511 keV. You do get 2 positive energy photons out of combined.
Oh, no, yeah, but the energy is always positive, but mass is antimatter and matter, right? So you can't create.
Even for antimatter, yeah. Even for antimatter, mass is still positive. But I just want to say that, you know, if you talk to particle physicists, they don't even distinguish mass and energy. Everything is measured in GeV, right? There is no, and again, it's since 1905 and E equals mc squared. Einstein told us that there's no point in trying to say that this is mass and this is energy, because they are the same thing. So I think it's a false kind of argument to say, oh, mass has gone into energy, because for more than 100 years, it's all just been energy anyway.
I was careful to say, not to say that mass is converted into energy, but that matter is converted into energy. I don't know if matter and mass are the same thing.
I don't know what matter is then.
That's a good question. I'd like to know that too.
I thought you were saying that light.
Our electrons matter.
Sorry?
In the conventional sense of what we're talking about in terms of matter, because
yeah, I guess that raises the question for me. What's the difference
matter
between an electron and a photon?
Yeah.
The one's got weight, apparently.
Yeah.
Mm.
I mean,
what about a neutrino?
Neutrinos have mass.
No, they don't. Do they? I have very little mass, virtually none.
Very little.
It's not the same. Light has no mass either. Is that not right?
Correct. Light has no mass.
Right. And what was being said earlier is that matter is. This is a great conversation because it's got nothing to do with Christmas lights. I'm loving it. And transparent.
We'll bring it back to Christmas lights. Don't worry.
No, but it's just very interesting to me because we're talking about the nature of light. I'm loving it because some people here have got some familiarity with the physics of light that I'm finding really intriguing. I will find continually intriguing to listen to because to me, it's a great mystery. I mean, is it a substance that is propelled through empty space that loses no momentum or ongoing, movement, velocity or whatever? No, velocity is part of what light is. So I just don't think that it's in any way can be conceived of properly as a substance that is thrust from a star through space, although that seems what it is. I don't think it is. So is it a disturbance in an all-pervasive field? I'm thinking that's what it is, isn't it? Isn't it a wave in the all-pervasive field? Is that what light is? I mean, I'm assuming it is, because that way makes more sense than a substance that goes on forever.
Yeah, I think that's how we understand it. I understand it as an oscillation or a perturbation or something in the electromagnetic field. If you get an oscillation in the electromagnetic field, that oscillation propagates through that field at a velocity which happens to be the speed of light, and that's all it is. It is just an oscillation in the field. But it's interesting. You talk to particle physicists, and they talk about electrons being oscillations in an electron field, and they talk about other neutrinos being oscillations in a neutrino field, and they talk about the Higgs particle being an oscillation in the Higgs field. I mean, every particle now has a field associated with it, and all the particles are really no more than perturbations or oscillations or something in the corresponding field.
That's a way of describing it in a way that's, I don't know, graspable by mathematicians, not me. That's a way of describing it, maybe a more convenient way of describing it for the mathematicians and the physicists. That's a way of describing it.
I think you're right. I think you're right. I don't think anybody knows what those fields are.
I think that's where I was going to go, is what's the field?
Yeah.
What is a field?
Tibor, you're saying that the field is prior to the oscillation.
Yeah.
You're making the field a kind of de facto ether.
Yeah, like a fabric.
I think we're getting a bit sort of tied up here with the way we're talking.
Well, but we do have a fabric of space-time, and we do have, if you like, virtual particles popping in and out of existence and doing all those things. That's all going on, if you like, in the background. And that is prior, that is a priori. What we see are the effects of some of that stuff going on. But I think that stuff is there. I don't think there's anything wrong with saying the fields are there first, and then there's an oscillation in there, which is the particle or the light or something.
That's what I'm doing. We're both philosophers, so we can make up this stuff.
But then, how much prior? Like, how many seconds prior is it?
Yeah,
it's there
guys,
forever.
I don't know, something I can't help wondering, and that is, I mean, Tibor, you would have been, I mean, as a philosopher, you'd be really fully aware of the veil of perception, right? And our inability to fully get to reality. Sure. So everything that we're discussing, right, is just, and we were talking earlier about the importance of language. It's just a model that we use to describe what our observations are. And the question that came into my mind as we were talking about the importance of words, talking about a ball bearing or a particle, talking about a wave, these are just objects that we know and understand. And I just can't help wondering, I mean, light seems to be neither. Yeah. It seems to, so the question is, if we use the particle analogy, or if we use a wave analogy as models to describe light, is there any possibility that that's actually putting a limitation on our ability to develop a new model that will describe what light really is? Because we can't get out of, it's either a wave or it's a particle, but we can't seem to move beyond that.
People are trying, surely. People are very dissatisfied with this wave-particle duality.
And I reckon that if one of the panelists has to put their name and put a hand up to talk, then we're probably talking too much.
Oh, yes.
So I just want to point out that physicists don't use this language, right? Physicists use the mathematics, and the mathematics doesn't say, is light a particle or a wave? There is the mathematics of quantum mechanics, and that's what you do, and that's where you make your predictions in. And you don't have one set of maths for light as a particle and another set of maths for light as a wave. You have the rules of quantum mechanics, and that's what you use. The problems only start when we want to cast it in a language which we think, we can make sense of in terms of our common sense ideas of what's a particle and what's a wave. But as I said, no matter how much we talk about this description, it's the mathematics which is important.
But let's
yeah, Geraint, I mean, we still in mathematics talk about a frequency of the light, right?
Yeah.
So we've got a quantity that speaks about the frequency, but if you talk about frequency, that immediately implies some kind of a, conceptualization of the thing.
No. I mean, when somebody talks to me about the frequency of light, I know exactly what that means. It means that when that light interacts with a material, and we're almost back to the question that we started the thing with, is that the electrons in that material will respond with a frequency of whatever that frequency is. They will start to oscillate up and down with a certain frequency. That's what the frequency of an electromagnetic wave means. It means how much do the electrons respond when the light arrives?
Yes. So in water, in the water molecule, the oxygen-hydrogen bond absorbs red light, which is what makes water look like blue, or ice looks like blue. A question that I have is when light travels through glass, I think the reason why the speed of light is slower in glass is because when light hits an atom or a molecule, it gets absorbed and then it re-emits light again. I'm careful not to say particle or wave. I'm just going to say it emits light, and then it bumps into another molecule. It gets absorbed. A little bit of time passes, and then it re-emits more light, and so on through the glass. I think that's what happens. Is that right?
I think so. Maybe not strictly, but I think that's roughly what happens. Certainly, when the light is moving through the material, it's not photons being passed from atom to atom. It's not a pass the parcel game the way Scott suggested. It's the energy of the light makes the outer electron of the closest atom or something resonate in a particular way. It picks up the energy, and it has a sympathetic harmonic oscillation that matches the incoming wave, and that oscillation, of course, has an effect on the electromagnetic field around that atom, and then it's the electromagnetic field which is going to affect the atom next to it, so it's going to respond. So you're really just propagating the energy through the electromagnetic field as the atoms respond to the energy as it comes through. And then at the far end, the last atom, in fact, radiates out the light, and it's a different photon, it's a different bit of light, but it has the same energy as what came in because it's been passed along from atom to atom. So in fact, inside the glass or material that it's passing through, I don't think there are actually photons in there. I think all that's happening is you're getting this movement in the electromagnetic field through the material, and then it becomes a photon when it pops out the other end, it gets radiated out into space, and then you think it's light again.
But a photon is just energy anyway.
Exactly, yeah.
And Mark had his hand up. Mark, go, off you go.
I just want to quickly say that, yeah, this is the issue that when I was in secondary school, the first thing I wanted to ask my science teacher and Form 1 was that if it's a fundamental property of light that its rate of that its velocity is 186,000 miles per second, or is so if light isn't moving, it's not light. It's intrinsic to it. So therefore, if you bounce a ball on the ground, it's in motion, but when it hits the ground, it stops. There's an absorption, there's an emission, there's whatever, and then it comes back up again. So in order to bounce a ball, there has to be a point in time when the ball is stationary. I asked that question, and my science teacher said yes. I said, well, then how does light work? If you point a torch at a mirror, the light is moving along really fast, the speed of light hits the mirror, stops, gets absorbed, gets emitted, and then comes out. Light has gone to a point of stationariness. And this is the question that I haven't yet had a satisfactory answer to, and which please anybody here can please offer some kind of answer.
Yeah,
Go on, Geraint. Yep.
Okay, So you have to remember that when light is traveling, you have to describe it as a wave. You can't talk about it as particles. You're not bouncing a ball off a surface. You have to think about it more like you've got a hose pointed at a wall, right? So when you've got a hose, water's coming out, it's bounced off the wall. You know that there's a little bit of that wave, that pulse of water, whatever's coming out of your hose, which is stationary as it's bouncing off the wall, but the entire water flow is still going. And the wave phenomenon is a continuous thing. It's not an isolated, it's the word that we use, it's not localized, it's not a point, it's a continuous object that you need to describe what's going on. So light doesn't bounce by photons behaving like billiard balls or ball bearings bouncing off an object where they're at rest. It is a continuous thing that's reflecting and interfering, etc., not an isolated object.
Well, there was a photon is an isolated object in some sense, isn't it? So
well, packet of energy. Look, another way to describe it, Mark, just listening to Geraint's description, it's a packet of energy, and the energy is being transferred. So the energy never reaches zero, and that's equivalent to when the ball hits the ground and comes up, you've reached an energy equals zero position. The energy of the photon never reaches zero, only its momentum is changing. So as it's transferring around the wall or the ground or whatever you're bouncing at the mirror, it is just changing its direction. The energy of the photon remains constant and discrete.
Yeah, and I think that's true even when you bounce a ball off the ground, in that when it hits the ground, the ball is distorted in shape, the bottom of the ball flattens out, and much of the energy is now inside the ball in terms of distortion and flexion and everything else in the ball. You've now compressed the ball, so the ball's going to push back. The energy is all there. It's just not now the energy of the global overall motion of the ball traveling to or from the wall. It's now the ball distorting in shape and doing what it does in the process of converting the energy in one direction to an energy in the other direction. But all the energy is still there. It's now just going on inside the ball at the time when it bounces off the wall. I think that's right, isn't it?
Again, it's all the different types of languages that we're using.
I love that nobody knows, but I appreciate the answer, Kevin.
I don't think it's nobody knows. I mean, if you asked me to write out the maths, I could walk you through the maths.
I would accept it. I would accept it. But all I'm saying, I'm just putting forward here the question that I had as a child, and which, like any other basic physics question, is not going to be fully satisfactorily answered unless I fully satisfactorily absorb the mathematical explanation of it.
Can I ask you a question? You've been to the ocean, surely?
Yes.
And you've seen waves wash against a seawall?
Sure.
Right? And you've seen how they hit the wall and bounce out again, etc.
Absolutely.
Right. So the water at the wall might be stationary, but the wave itself is just happily moving, right? Bounces in, bounces out.
Well, I assumed there was a momentary, I assumed there was a point at which that it came to a halt before turning around and coming back the other way. I thought that was true. That was true of everything.
No, but it's only part of the wave is doing the turnaround, but the rest of the wave is traveling in, traveling out, interfering and doing more complicated things.
But the only reason it gets to travel out, apparently, is because it gets absorbed by matter, which then, re-emits another wave. That's not the one that came in, right?
I think there's a conservation of momentum going there as well. So the momentum of the wave as it hits the wall is transferred into the wave, and then the momentum of the wave goes back the other way. So the momentum of the wall is going in the way of in the direction of the original wave by 2 times the momentum.
If the wall is solid enough and doesn't move, then
it does move.
When the ocean wave crashes into it, the wave actually, the water in the wave actually moves up and down. It becomes gravitational energy. The wave is pushed up, and then when it comes back down again, the wave propagates back out, and you can see that happening at the stone wall. So most of the energy doesn't go into a vibration of the wall. A little bit of it might, but if your wall is solid enough, there's not much of that going on. Really what happens is the water changes direction. It hits the wall, it can't go further, so it then goes up, becomes gravitational energy, then it falls back down again and propagates away as the reverse wave, I think.
Yeah, I think we've got to be
I'm not
really
sure.
careful of that. No, I wouldn't. I don't agree with that. In fact, what's really happening with the wave traveling through the water is the water molecules are just going up and down. There's no lateral movement in a true wave. So really what's happening is that the energy is traveling through the water, lifting the wave, the molecules up and down in the water. When it hits the wall, it's the energy that just simply inverts in its direction and goes straight back again at exactly the same speed as it hit the wall. But it's not actually anything that's hitting the wall, because all that's happening again of the molecules of the water that's against the wall, all they do is move up and down. That's all that's happening. So we can't confuse the movement of water matter with the energy that's traveling through the water.
So bringing it back to light again, if you take a laser beam and you shine it at a mirror, then the mirror recoils. So
yeah, it does deliver momentum. Yes.
Yeah.
Can I? Sorry, I'm just going to jump. I'm going to jump once back to water, and then we can move on to light. Water doesn't move up and down in a wave; it moves in a circle.
Yes.
Right. So a water molecule travels in a circle as a wave comes through, and when it hits the wall, there's a momentum transfer because it can't travel in a circle anymore, and that's what causes the reflection in the wall. But for light, I promise I'm going to get back to light. For light, what happens, of course, is that when that light hits the wall, the electrons start to oscillate and they produce their own electromagnetic waves, which propagate outwards, and they interact with the incoming wave, and that's what gives you your refraction and your reflections, etc.
I didn't mean it as an absolutely literal analogy. Just the fact that if something is going in one direction, it has to come back another way. It has to undergo a moment of stationariness, which is this. I'm not harping on about that, but I leaped in with it when it was mentioned earlier that the way that transparency works is that the light particle, wave, whatever, enters the material and then is absorbed by an atom and then re-emitted and then absorbed and re-emitted. And this is what causes the slowing down of light through the material. If light is slowing down because of this absorption and re-emission, one imagines that to be absorbed and to be re-emitted takes some time. Therefore, the speed of light slows down at the surface of a mirror. That was what I was thinking about. Well, let's not go on about it.
But that's not correct.
Yeah. Okay, I accept that.
Yeah. So when light hits a material, sorry, I'm talking a lot here, so I'll shut up after this. When light hits a material, the electrons start to oscillate. They emit electromagnetic waves with the same frequency as the oscillations, and those oscillations interact with the rest of the electromagnetic field. And the net effect is that the wave appears to slow down. Light still travels at c, but the interference pattern is a different speed to light traveling in a vacuum. So it's as Scott was saying, it's not that light gets passed from one atom to another atom, but you've got the electromagnetic wave, and then you've got all the electromagnetic waves from all of the electrons all interacting together, and the net effect is that it looks slower. And now I'm going to shut up.
Here's a question. And Kerry would know this, if you've got a laser beam and you point it at something, you get a little dot, right? And then if you look at Kirrili's backdrop, and it's a Christmas tree. We didn't see that before.
Yeah.
And also she talked about her favorite phenomenon being double slits. So the question is, I guess, is how wide is this photon? Because on the one hand, it comes out of a little aperture at the front of a laser. So you might say, well, photon comes out of that aperture, so it's only that big. But then you get slits, and then you get things as big as prisms. So how wide is a photon, if that even makes? I know the answer is it doesn't make sense, but
is it related to the wavelength?
Yeah, I have a related question, which relates to what you're asking. With radio telescopes, I noticed with the radio telescopes on the outer rim, it's not a solid, but it's a mesh. But still reflects. I think that might be related.
Yeah, well, what I was going to say was, you know, the width, height, any dimension is related to the wavelength. So which is a wavelength is just synonymous with energy, or frequency. So if you have a very high energy photon, it will have a shorter wavelength. I feel like some people have stopped moving. No, they're back.
No, we're here.
Okay, everybody just froze on my screen, and I'm thinking I'm talking into the ether. No one can hear this glorious piece of physics being spouted from my mouth.
So Kirrily, if I have a long wavelength beam of light, say a deep red or infrared or something, and I have a very narrow slit, does that mean that the slit can be so narrow that the light doesn't get through because it's somehow thinner than the wavelength of the light? Is that what happens?
Go on, Geraint.
I don't think so.
So sorry to jump in again. I'm talking so much. It's all to do with how much the electrons can respond, right? So if you look at a Faraday cage, which of course is a metallic cage, it can stop radio waves because the electrons can oscillate enough in the cage to match the incoming waves, but light can get through because the electrons can't oscillate with the right kind of motions to block light out from traveling through the cage. So it's dependent upon the wavelength and how much the electrons can respond. And if you have an electron and you can stop it responding, if it's held in place, then the material is transparent. Light can travel through because the material cannot respond. Have I gotten back to the original question?
No, but I'm really glad because you just made me think of something, because that phenomenon I've seen in experiments on laser-driven particle acceleration and laser plasma interactions, because this plasma frequency or electron frequency is all to do about how we understand how intense laser pulses propagate through the targets. And we do see an onset of relativistic induced transparency, where your laser matter interaction is so intense, your electron oscillations are so intense that their mass increases because they're now into the relativistic regime, and you end up with a change in plasma frequency, which then induces this onset of transparency. And so we've seen that effect in the lab. We can see when that happens. We've studied it in simulations, and now we've actually seen it in experiments as well, that you can tune the conditions between the laser photon interaction and the thing that you're shooting, and actually see a change in onset. It doesn't happen instantaneously. It actually is to do with transfer of energy between the laser and interacting of the laser's EM fields with the plasma electrons. They become relativistic. That increases their mass. That decreases their plasma frequency, and all of a sudden, your critical density goes up. The critical density is the density that's needed to stop a laser from propagating because of this interaction between electron fields and EM fields. And we'll see. And what we see that experimentally, the evidence of that is that we see more of an exchange between the laser energy and the electrons that are actually ejected or accelerated, and we see a boost in that particle acceleration by that method. So yeah, relativistic transparency, it's a thing, it's real, it's great. But only obviously it was extreme. We're talking like 10 to the power 21 watts per centimeter squared.
Wow.
So that's about a petawatt laser focused down to about a micron spot, a couple of hundred joules delivered in a picosecond, or tens of joules delivered in tens of femtoseconds. But
Wow.
shooting very thin foils, nanometer thick foils. Yeah,
that sounds it's a pretty extreme experiment.
Yeah, it's very good. But it's really nice to demonstrate those fundamental concepts.
how we haven't created a black hole that sucked us all in yet, I just don't know. Yeah.
You know, Einstein talks about the speed of light, you know, the famous equation. Is there anything, is the speed of light just arbitrary? Is it tied to anything, or is it, or do we just measure it and it's that number and that's like, okay, well, that's the number? Or is it a special number?
Well, if it's related to what Maxwell said, then it's related to the permittivity of free space, and it's a function of some property of the fabric of space-time, which is the permittivity.
No.
You don't think so? All right. So how does that work? Is it the other way around?
It's the other way around.
Is it? So how does it work?
Well, with the permittivity and the permeability are observer dependent, because your observers disagree on what's electric and what's magnetic. So the fundamental thing is the speed of light, not the permittivity and the permeability. So, but to go back to Scott's question, the answer is, it's arbitrary. We don't know why the speed of light is the speed it is. We don't know why it's 300,000 kilometers per second. And in fact, you know, we're coming up to Christmas, and I have a book on this very topic about the, you know, fine-tuning of the fundamental constants. In that this is one of the numbers that we have to ask nature for. We can't do physics until we ask nature what is the speed of light, and it tells us. We can't work it out. We can't get a mathematical expression where it's pi squared over 4e to the whatever. It's a raw number that we have to get from nature.
And are we convinced it's the same everywhere in the universe?
I'm reasonably convinced. I have a colleague who used to be at NSW who was less convinced. He claimed yet evidence that it had changed slightly over the entire history of the universe by about 3 kilometers per second over 10 billion years, which is not a lot. And there are limits from a natural nuclear reactor in Africa, the Okolo reactor. So you can do this by measuring a number called the fine structure constant, which is the thing that tells you about the strength of the electromagnetic interaction. And that appears not to have varied across cosmic history. So it appears that the speed of light has been the speed of light throughout the history of the universe, as far as we can tell. There's some dodgy evidence right at the fringe, but yeah, it looks like it's been about the same number.
Surely it's related to the nature of space and time. And
in what sense?
Well, being completely fundamental, and you can't measure speed or velocity or whatever, speed of light, except in terms of space and time. And given that we're in a universe that apparently has got a bit of space in it, and that we must comprehend, we must have a notion of time in order for motion to even exist, to our understanding. And then space and time, given that they are part of this universe, then in this universe, the speed of light, I think, intuitively, has to be a precise, exact number. Whatever it happens to be, it is because of the reality and the nature of space and time itself. That's what I'm assuming. You don't agree?
It is a number that relates space and time, but why it is the number it is unknown.
Okay. But there has to be...
Geraint, I've got a slightly different question for you. The speed of light, as you say, is a fundamental constant. It just is what it is. But doesn't it determine basically how clocks work?
Yeah.
Now, if that's true, then isn't it somehow self-referential in that if light was slower, the clocks would go slower, and you still think the speed of light was the same number because they both slow down the same amount? So if you define clocks in terms of time, in terms of light, and light in terms of clocks, or speed of light in terms of clocks, then really saying that the speed of light is a constant is really saying that we will always observe it as going at the same speed. Because we're always going to use a clock to measure it, and the clocks will compensate for the difference in the speed of light. Is there something circular going on in there?
Slightly, except not all clocks tick at the same rate. So one of the reasons that you can measure the speed of light across the universe is because some atomic transitions depend upon the fine structure constant to different powers.
Oh, okay.
So the fundamental clock, which you might say is the fine structure constant, different clocks use it differently. And that's how they can use it to measure the speed of light in different parts of the universe.
Okay.
I will cite John Webb, who used to be at NSW, who did a lot of work on this. I'll find a paper and I'll post it in the chat.
Okay.
And also, I think we were talking about just before it started, the implication of it traveling at the speed of light is it doesn't experience time, which is freaky.
Well, the thing that I have a really interesting question about this, guys, and that is, if you have a look at the whole of Einstein's theory, it's all about what's happening relative to the observer. When you have a look at quantum mechanics and the uncertainty principle, it's what happens when you make an observation. So somewhere it's beginning to feel like the observer is a very, very important part of what's happening in reality.
Well, that's the only access we have to the world. We only have access to observables. And it is from those observables and patterns in those observables that we try and make inferences about what might be out there. You never observe what's out there. You only observe your interactions with it, and you only observe what you can observe. So that's one of the problems that philosophers have been tackling that question for thousands of years, that you really don't have direct access to the facts, so to speak. You haven't got purchase on reality. All you've got is a bunch of observations and a bunch of observables. And it is from that that you have to try and reverse engineer what you think the world must be like.
Yes.
Yeah, and I mean, I think that observation, Tibor, is very close even to what we've discussed tonight, because one of the other things that I often talk, kind of speak about sometimes, and that is, if you try and think of what is the color of radio waves, we can't imagine because we can't perceive them, right? At the end of the day, if you think, we actually used that tonight, really long waves like infrared or red rays, right? Very long. So, but the thing is that if you think about the color of a radio wave coming into your eye, we cannot imagine that there's a color associated with it. And in exactly the same way, a red light is just electromagnetic wave. So that basically means that the color red is something that's created in our heads.
That's correct.
It's generated there, right?
Yep.
There is no color red in reality.
That's right.
There is no color in the world.
That's right. The universe is colorless. It's absolutely right. What happens is there's electromagnetic radiation of different wavelengths and frequencies and stuff, and your brain decides to interpret some of those differences as different colors, but you're making the colors up. There are actually no colors out there. I think that's again a theory of qualia. We've got that in philosophy. Yeah. We've had that nailed down for a while. Yeah. So we know there's no color.
Yeah.
Can I just jump in here, because we're talking about perception, to go way back to the beginning when Geraint was telling us I believe quite correctly, that just because the sun had particular kind of frequencies and that we evolved to be around to perceive those frequencies. I wanted to say about that we have like 3 photoreceptors for red, blue, and green, but that birds and butterflies will have 4 because they can perceive ultraviolet. But the interesting thing is this little crustacean, which I think is found on the Great Barrier Reef, which is called the mantis shrimp. Okay, and it can perceive all the visual range plus the UV, but it also can perceive polarized light and circularly polarized light. So for some evolutionary reason, this mantis shrimp outdoes us by a huge amount. So it has this wonderful kind of, well, we have no idea how it feels about what circular polarized light will be, let alone all the other things. So it's not like we reign supreme. We may have better vision than dogs, and cats and dogs or something for colour, but we don't do that well for others compared to others.
Yeah, that's absolutely right. Actually, that prompts me to ask about polarized light. One of the things I find fascinating is polarized light, which is why I mentioned birefringence. It's hard to say. I can understand that if you've got a crystal like a calcite crystal, then as Geraint says, the electrons respond to the incoming light and they oscillate or they respond in different directions, and so you get the light breaking up that way. I can understand that. But the concept of circular polarized light troubles me. I just don't understand what that is. How can something be polarized in all directions at once? Isn't that the same as just not being polarized? What's circular polarized light?
It's light where the polarization vector rotates. So polarized light has an orientation up and down, okay, or that way, or that way. Circularly polarized means that the vector actually rotates around. So it rotates around with a certain frequency. So it's not random, it has a particular pattern to it.
So at any instant in time, at any point in space, it's polarized in just one direction.
Yeah,
as it
that
moves,
changes.
So as it moves along, it twists as it goes. That's what circular polarized light is.
And
Yeah.
is that a fixed helix, Geraint, or is it? Can you get, like, for a certain wavelength of light, can you get different periods of?
Yeah, it's wavelength dependent, right? Isn't this what Faraday rotation does when it goes through a medium? You get this splitting of the polarization. So you get different amounts of rotation. Something like that. I just posted a thing to the chat just to note that this is something I only discovered recently, is that humans can actually see polarized light. And you can see it with the computer screen. So there's an effect called Heidinger's brush, where check out this web page and get your screen up. Later on, you can see polarized light coming from your screen. We are weakly able to do what the mantis shrimp can do.
Okay, great.
And could you explain why in old photography we used polarized filters, but in digital photography we use circularly polarized filters?
In normal photography, I mean, you use a polarized filter to get rid of glare, right?
That's right. But when we move to digital cameras, the polarizing filters are circularly polarized.
That I have no idea about.
Yeah.
I haven't got that far. I've never put a filter on a digital camera. Well, I have put it on a detector on a telescope, but not for circular polarization. I don't understand why you would have that unless.
Yeah, I understand why it was either. I think it must be the way the pattern of the pixels in the in the photoreceptors or something.
Yeah,
And do you get circular polarization quite commonly in astronomy?
No, it's relatively rare. So you to produce circular polarization, you need something going around in a circle, and normally that's electrons in a magnetic field. And so there are places in the universe where we have that. We have them in near black holes where electrons get spat out and they spin around. So that produces circular polarization. One of the most intriguing things is that there was a theory by a guy called Jeremy Bailey, who I think might be still at Macquarie University, that that humans have a handedness to our molecules.
Yes.
That we prefer one molecule to another. So there is a handedness to all our molecules. And he claimed that came from circular polarization in the gas cloud in which the sun and the earth were formed, because that preferred some molecules to other molecules. So the fact that we can take the same molecule and have the mirror images and they taste different is related to circular polarization in the protostellar cloud 4.5 billion years ago, maybe.
Wow. I'm sure people went
But we have to find a way to explain it, right?
Yeah.
Because normally those molecules are 50-50 in nature.
That's true. But then I read somewhere that people think the whole universe is somehow left-handed or something. There's some sort of handedness to the whole universe.
Yes.
I understand it. I understand it locally. That makes sense because yes, we do have left-handed molecules in preference to right-handed proteins in our bodies. But is the whole universe? Does the whole universe exhibit some kind of handedness?
It's been claimed. People have claimed that in our observations that the universe has a handedness. It normally comes down to bad statistics.
Okay.
Could it be a sign of intelligent communication if it was obviously not a black hole sort of thing, but to produce some sort of beam in space?
There would be easy ways of doing it. You could modulate the frequency.
Yeah,
and
you could modulate.
transmit
Yes,
triple J across the galaxy, right?
That's
Rather
right.
than
That's right.
worry about circular polarization.
Mm.
Again, I've been talking too much. I'm going to hand back to Scott.
Well, I think maybe we're about that time, so maybe we'll call it there. I was anticipating that we might get on and talk about the 2022 Nobel Prize, which sort of comes onto this thing about polarization. But maybe I think if we're going to convene some of these next year, maybe we'll do a whole thing on the Nobel Prize. It's very deep.
I brought out Anton Zingler to Australia, to Sydney Uni years ago. I organised his tour, for the Centre for Human Aspects of Science and Technology. I organised his tour from Austria out here to give a public lecture.
Awesome.
Good.
Yeah.
Maybe you can invite him along then to our Zoom.
He can be the special guest.
And Scott, maybe we should look over some of the more historic Nobel Prizes.
That's a great idea. Yeah.
A Nobel
Excellent.
Prize session. Why not?
Yeah. Okay. Well, thank you, everyone. That's been fascinating. We covered some strange areas there, which I didn't anticipate at all. But it's been great fun, and thank you very much. Have a very a Merry Christmas and a great rest over the holiday period, and we'll see you bright and bushy for Zoom into Physics in 2023.
Thank you.
Excellent. Thanks, Scott, and thank you, everyone.
Bye.
Thanks
Merry
very much,
Christmas,
guys.
everyone. Bye.